In this video, we're talking about central limit theorem, and we'll be using Rguroo as our technology. So the central limit theorem is one of the most profound and useful results in all of statistics and probability. And the idea is similar to what was in the video that I paired with this one that involves the bunnies and the dragons. But basically, you take some quantity that isn't necessarily normally distributed. In the video, it was dragon wingspans. Those were bimodal. And if you take a large sample size and find the average wingspan in that large sample and record the average, and then repeat that, take another sample and find the average of that sample and record that average, and then another, and then another, and then another. And if you take the records of all those averages and use them to create a histogram, you'll see a symmetric bell-shaped distribution. So that is true for any type of distribution, whether it's normal or not. The distribution of sample averages, if the sample size is large enough, will be normal. So if we take a large sample size, and we're going to define a large sample as a sample bigger than 30, the sample means will follow a normal distribution. So we have some new notations that we need to learn. And the first notation is the mean of the normal distribution. So the mean of this type of distribution is called the mean of the sample means, and it looks like this. And so the mean symbol is mu, something we're familiar with, and then the sample mean notation is x bar, also we're familiar with. So when we put them together, a mu with a subscript x bar, it stands for the mean of the sample means. So the mean of the sample mean distribution is actually equal to the population mean. So that is important to note. If you know one, you pretty much know the other. And then the standard deviation of this type of distribution, again, the standard deviation of the sample means, the distribution of sample means, is the same as the population standard deviation divided by the square root of the sample size. So this formula right here. So you definitely want to write both of those down. Now notice the notation for the standard deviation of the sample means. It looks like this. So standard deviation sigma, subscript x bar. So standard deviation of the sample means. Now, what do we call this? We actually don't usually say the standard deviation of the sample means. We could call it standard error. So from henceforth, when we say standard error, we are referring to the standard deviation of the sample means, which is standard deviation over square root of n. So basically, if you know those two facts, you know that if you take a large enough sample and you took a large number of samples over and over and over again, that the means would form a normal distribution with a mean that is the same as the population mean and a standard deviation equaling to the standard deviation divided by the square root of n. Then you can use the technology we used before to find proportions and probabilities using these facts, using these properties. So let's take a look at what I'm referring to here. So the mean age of college students in 2008 was mu equals 25 years with a standard deviation of 6.8 years. Now that is the mean of the population and the standard deviation for the population. Moving on, a simple random sample of 64 students is drawn. What is the probability that the average age of students in the sample is greater than, and actually, let me move this a little, see if it'll let me move it. I'm thinking it's greater than 26, and it got cut off from the screen here. And it's not letting me move it. So what is the probability that it is greater, let me write that out, greater than 26? Okay, there we go. So, just kind of like breaking this down, we know that the mean is 25, population standard deviation is 6.8, but the question has to do with the average age of students in the sample. not from the overall population. And so what we can say is that when you have a sample of 64 that is bigger than 30, that if we were to line up the sample averages would line up and form a normal distribution, with the mean being the same as the population mean, which happened to be 25. And then the standard deviation would be the standard deviation of the sample means, which is the standard error, would be the standard deviation over the square root of n, which you can see I used a calculator to calculate that here. Now, where did I get that from? I just want to show you real quick. On Rguroo, if you click on Applets and Calculators at the bottom, and then Maximize Calculators, and then you can either do the scientific, the full functional, or the graphical. I'm just going to click on the first one, and then I just type that in, 6.8, which was the standard deviation, divided by, and then click the square root sign, and then, what was it, 64? And you get 0.85. So that's where that came from. And it's nice that that's built right into Rguroo. So when we are trying to find the probability that the average age, if we took a sample, right, and we're trying to figure out the probability that the average age of that sample would be greater than 26, so we know that it forms a normal distribution, and we know 26 is somewhere around right here, and we want to know the probability that it's greater. We can use the functions in Rguroo we used before. So we can use the probability calculator, and we can do values to probability with a normal distribution. The mean is 25. The only difference here is you don't put in the standard deviation, you put in the standard error, which is the standard deviation divided by the square root of n. So you have to calculate that first, which is why I usually pull up the Desmos calculator, calculate this, and what I do is I copy this and paste it right into here. So I don't even have to type this out. I just copy and paste it right there. Makes it so much easier. And then the rest should be similar to what we did in the previous video. We want above 26. So above 26, click graph, and let's go do that on the actual Rguroo screen. So if I hit probability and simulation, probability calculator, choose continuous, we're doing values to probability, normal distribution. The mean we said was 25. And then let me show you what I meant. I still have the scientific calculator open, so I'm going to toggle back there, and I'm going to go over here to this 85, and I'm going to highlight it, right click it, hit copy, and then toggle back over to the calculator here, and then I'm going to, in where it says standard deviation, I'm going to do Control V, and which pastes, and look at there, I didn't even have to type that in. And then we're finding the probability that it is above 26. And you can graph it if you want. And the probability that it is above 26 is 0.1197. 1197. Okay, so it's very similar to what we were doing before. The questions are going to look similar. It's just that the questions are going to have to do with the sample averages usually, because we're dealing with sample distribution. So again, if you take large enough samples, it doesn't matter what the distribution of the population was before, but the sample averages will be a normal distribution if the sample size is big enough. All right, so we actually just did this one, and there was the answer right there. It's the same thing we got before, but I just pasted the screenshot in there for you. All right, let's look at the next one. If the mean weight of a bull is 1,135 pounds with a standard deviation of 97, would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So first off, it doesn't say anything about a normal distribution here, and if you think about it, it doesn't have to, because if the sample size is big enough, in this case, what is the sample size? It's 100 head of cattle. Then we know that the sampling distribution, if we took a large number of samples, and then we put all those sample averages into a histogram, it would make a normal distribution. That's what we know. And the question is, would it be unusual for the mean weight? So we're talking about the average again, the mean weight of those samples, the sample specifically of 100 head of cattle. So I'm going to go ahead and draw here. In the middle, I have the mean, which is 1135. And then the standard deviation, remember, is the standard deviation of the sample distribution, which is standard error, is the standard deviation over the square root of n. So it would be the standard deviation over the square root of n, which is 100. You're going to get 9.7. But I'll show you how we do that with the calculator again. I'm going to go back to, again, under Appleys and calculators, choose one of the Desmos calculators. Any of them will work. And I'm going to type in 97, division sign, square root, 100, and you look on the right and you get 9.7, which you can cut and paste into the calculator. Okay, so going back here, would it be unusual for the mean weight of 100 head of cattle to be less than 1,100? So 1,100 pounds is somewhere around right here, and less than that would be this direction. All right, so we're going to do the probability calculator. We're going to do values to probability. It's going to say normal distribution with a mean of 1135 and a standard deviation of 9.7, and we're going to do below, oops, I misspelled below, only one else, below 1100. That's what we're typing in. So let's go back here. And I just toggle back over to my calculator, and I can just hit basics and then change everything there. The other thing I could do is I could just start over and go to the probability simulations tab, click on the probability drop down, probability calculator, choose continuous, make sure it says values to probability. The mean was 1135. And the standard deviation is 9.7. I can also cut and paste that, or copy and paste that 9.7 there as well. And I want to do below 1100 graph if you want to preview. Now, this one you don't see any shading, and the reason is because 1100 is so far below the 1135 measured in standard deviations that you can't even see the shading. So there's shading there, you just can't see it. And if you look at the probability here, it does confirm that the shading is small. It's 0.000151. So 0.000151. Yeah. And then if you were to round this to 4 decimal places, let's say it'd be 0.0002. So would it be unusual? So the reason we found the probability is because would it be unusual? Unusual is any probability that's less than 5%. So it is less than 0.05. So yes, it would be unusual. That's why we found the probability to start with. All right, moving on. Gas mileage. The EPA rates the mean highway gas mileage for a 2011 Ford Edge to be 27 miles per gallon. Assume the standard deviation is 3 miles per gallon. A rental car company buys 60 of these cars. Here's your sample. Right there. So what's the probability that the average mileage of the fleet, so the fleet would be the fleet in this sample, the cars in the sample, is greater than 26.5. So again, the mean goes in the middle, which is 27. 26.5 is somewhere over to the left, and we want the probability that it's greater. And so we just need to remember that the mean of the standard deviation, the standard deviation of the sample means is 27, the standard deviation, which is 3 over the square root of 60. And we're going to do the probability calculator. We're going to choose continuous. We're going to do a normal distribution. We are going to do a mean of 27 and a standard deviation of 3 over square root of 60, whatever that is. And we're going to go above 27. That's what we're choosing. So I'm just going to go back to basics and change these things here. So my mean is now 27. And my standard deviation, I don't know what that is. So I'm going to toggle back to my calculator. And I'm going to put in the standard deviation, which is 3, divided by the square root of a sample size of 60. So we get 0.38729833346, and we could round that, but the farther you take it out, the closer it is going to be to the actual calculation. So I just copied it, and then I'm going to paste it here into my standard deviation. And then we're doing above, what are we doing? Above 26.5. And we can see above 26.5, it has a probability of 0.9016. 0.9016. Okay, so next question, what's the probability that the average mileage of the fleet, again, of the sample, is between 26 and 26.8? So same thing. We're just going between 26 and 26.8, wherever. Actually, both of those are actually below the mean. So the shading, it would be in between, but that section would be farther to the left. I'll show you what I mean. If we go back here and go to basics and change it to between, and we're going between 26, the lower tail would be 26, and the upper tail would be 26.8. And the mean would be 27, and the standard deviation, again, was what we got when we divided 3 by square root of 60. Check out the graph. There is shading between, but you can see it's further to the left because both of those numbers are below the mean. And that probability was 0.2979. All right, so would it be unusual if the average mileage of the fleet were less than 26 per gallon? So unusual means we need to find the probability and that it's less than 26. So we're going to do the same thing, but we're going to choose below 26. So I'm just going to go to basics and hit below because I don't need to change the mean or the standard deviation here. All of that's the same. Below 26 would be 0049 12, which is less than 0.05, so it would be unusual. Yes, it is unusual because, again, if the probability is less than 0.05, then it would be considered unusual. And then just going back here, we did mean of 27, standard deviation of 3 divided by square root of 60. We pasted that in. We went below 26. And that average being less than 26, that probability was 0.04912, which is less than 0.05. All right, what's next? Last example, NYC rent. The real estate group in NY reports that the mean monthly rent for one bedroom apartment without a doorman in Manhattan is $26.31. Assume the standard deviation is 500. A real estate firm samples 100 apartments. So there we go. We have sampled 100 apartments. We can tell you, though, that the distribution of those sample means have a mean that is the same as the population mean, 2631, and the standard deviation of those sample means, the standard error, is the standard deviation of the population divided by the square root of the sample size, so the square root of 100. And this one I could actually do fairly quickly by hand. We end up with 50 there. Let me just show you, double check. If I went back to the calculator and I did 500 divided by the square root of 100, I get 50. Okay, so what's the probability that the sample mean rent would be greater than 2,700? So 2,700, we'll say, is right here. Greater would go that way. So again, we're doing a probability calculator, normal distribution, a mean of 2631, and a standard deviation of 50, not 500, 50. Okay, and we're doing above 2,700. So toggling back to my calculator, we did probability calculator chose continuous. This pops up, values to probability. The mean is 2631, and the standard deviation when we calculated it was 50, because it's the standard deviation of the sample means, rather, which is the standard error, and we're doing above 2,700. And we get that probability is 0.08379, which rounds to 38. All right. Next, what's the probability that the sample rent is between 2,500 and 2,600? So between those two. So same thing, the mean is still 2631, standard deviation is still the standard error, which is 50. So we just go here and we change the above to between, and we're going between 2,500, and the upper tail would be 2,600, between 2,500 and 2,600, and we get that is 0.2632. Right. All right, so now we're switching gears. Find the 60th percentile. So if you'll recall, the 60th percentile is the boundary that separates, oops, let me do this again. 60th percentile is the boundary that separates the lower 60% or 0.60 from the upper 0.40. So they're giving us the probability, and we are looking for the boundary for that. So this time we are going to do probability to values. And if we put in 0.60, that's the lower tail. So this is the lower tail, and this side is the upper. So if you were to do lower tail, you need to put in 0.60. Upper tail, you need to put in 0.40. The mean is still 2631. Standard deviation is still 50. Oops. Sorry about that. Wrong thing. Clicking over here. Basics. Mean is still 2631. Standard deviation is still 50, but you want to choose probability to values this time. And we're doing lower tail, which is 60%. So you got to put it in as a decimal. So 0.60. And we get that is 2643.67 would be this boundary here that separates the lower 60% from the upper 40%, which is the 60th percentile. Would it be unusual for the mean to be greater than 2,800? So anytime they ask about unusual, you're looking for a probability. So we need to go back to values to probability, and we're going above 2,800. And Let me just quickly go back here so you can see that because I forgot to move back to this screen. So would it be unusual for the sample mean to be greater than 2,800? I drew it out. We're doing values to probability because anytime we talk about unusual, you got to find a probability and see if it's less than 5%. So we want to do above 2,800. And everything we've done so far has been unusual. You can see, you can't even see the shading, it's so small. So 0.00, the probability is 0.00036, which would round to 0.004, which is less than 0.05, and it's less than 0.05. It is unusual. It is unusual. All right, so do you think it would be unusual for an individual apartment to have a rent greater than 2,800? So with that, they're talking about an individual apartment. So an individual apartment, you're only choosing one. And that would just be, you could look at it two ways. You could look at this as the standard deviation of the sample means would be the standard deviation over the square root of the sample size. And in this case, the sample size would be 1 because it's an individual. And so you end up with 500. Or you could look at this as going backwards. When you find the area under a normal curve, it does tell you the proportion of the population that falls between 2 points, but it also gives you the probability if one is randomly chosen, if only one is randomly chosen, that it would be between the points given. So we could just go back and just use the regular standard deviation here. So we're doing greater than 2,800, which we already have in here, but we want to change the standard deviation back to 500, or 500 divided by square root of 1, which is still 500, and it would be 0.3677, which would not be unusual because it is not less than 0.05. And that's all I have for this section. So if you have questions, please let me know.